So we're going to get into the material. What I'm going to do today is, for those who actually did not attend, I'm just going to do a quick review and recap of what we covered in the first part, which was MLflow tracking. And then there's a YouTube video. You can actually see the link over there. And I also posted the link on the chat, so you should be able to actually get to see this. And I'm going to talk about the two other components which comprise the platform called MLflow projects and models, and discuss, what's the motivation behind that? What was the reason that we actually need projects and models and how they actually fit into the grand scheme of things? And then we'll discover how you can actually do model execution on a Databricks Community Edition. Hopefully, most of you will have signed in. And then we'll explore how you can actually use the MLflow UI built in as part of the Community Edition, so you can actually compare and contrast the model execution, the people that shared the models with you, that you can actually compare and run different runs. The two URLs that you actually see are the GitHub that you will actually need. So go to that particular URL, either clone it or keep it open and use a browser to get to the material that you actually need. There's also a directory under there called slides, and the slides has all the PDF that you actually need if you want to follow me online. I believe somebody in QA posted, do we actually have slides for this? So the slides are in this particular GitHub URL. So the first one is the GitHub URL. The second one is the project that we're going to execute. So keep those in mind. Okay, now just a quick review. Last one, the last workshop that we did, part one, we started with an assertion. I made a claim that machine learning is complex, and the complexity is not so much from the fact that the algorithms are difficult, or the math or the theory behind it is difficult, or the languages and the frameworks are difficult. The problems stem from two different sources. One is the methodology, and the second is how the model evolves over time, and different stages of the model development require and demand different requirements. And because of those two, the whole process actually becomes quite difficult. So let me just recap very quickly what those are. The first one is the methodology. What I mean by methodology is that how do you go about, what is the modus operandi you actually use to do traditional software development for machine learning? And I think those are quite different because the goals are very different, right? In the traditional machine development, you actually have a specification that you actually go through and you write to this particular specification. Whereas in the machine learning, you have to optimize the metric. You're more concerned about how can you actually make the metrics, what can you use to move the needle so you can actually deploy this model with confidence that you have a reasonable accuracy. And the second is that the quality in the traditional software development depends only on code. Well, much of it depends on code, whereas the quality in the machine learning depends on your input data and your tuning parameters. This is not to say that the code quality doesn't depend on the machine learning code that you write, but I think that will be determined by, what's your input, how large is your input, what are the tuning parameters that allows you to do regularization, or what are the tuning parameters that you actually use to make sure that your model is generalized and as a result of that gives you a good metric. And the final thing is that in the software development cycle, in the compile edit cycle, there is a limited stack in number of libraries and number of tools and utilities you're going to use. It's pretty much limited what your company's infrastructure supports. Whereas in machine learning, it's slightly different because you want to compare and combine many libraries to create a particular model that gives you the ultimate, the best model. And those are the ones that you actually want to use, which are most recent, which has a large community around it. And they're sort of, a good part is open source. So I think that's problem number one. The second one is that if you look at the quintessential cycle of how machine learning preparation of model evolves, you got all these different stages, and each and every stage will have a myriad set of tools that you're going to use, right? So for data preparation, you might be using a combination of tools to do your ETL, or to do your feature engineering. You might use scikit-learn, or you might use pandas, or you might use Spark along with SQL, or you might just use pandas as a programming language, or Scala, or whatever. And then if you're training, as I say, the machine learning cycle demands that you just not use only one library, but you have the option, you have the ability to use other frameworks as well, so you get the best of the world. And then the third is you might be deploying in different form factors. You're not only limited to one, you'll have several deployment targets you actually want to do. And then finally, your data ingestion as well is complicated. And so that's the one thing. You have different set of tools and they have different requirements. The second part is the tuning. Each of these tools will have specific tools and configurations you actually want to maintain. And more importantly is the tuning part in the training model. You actually want to make sure that you probably use the best hyperparameter tuning that you have scoped over the entire space. And so that really affect the needle, because that's what you want to do. You want to optimize the metric. And one of the things you do that is by constantly experimenting with new parameters, new tuning, so that you get the best model. The third thing you have to do is you have to do it at scale. Each of these stages require that you actually do it at scale. And the scale comes into the form, into prominence because of the fact that we are dealing with the large magnitudes of data in today's era of big data and ML. So the scale is important. And then third and final is model exchange. How do you ensure that the model that you tune, the model that you train, the model that you were satisfied with that has an accuracy is easily transferable in the same way that you actually train? So model exchange is important. And then last but not least, we are living in the world of data privacy, and we have to worry about governance. We have to worry about provenance. So how do you actually account for all these? And as a result of these two distinct sources, machine learning in general actually becomes a bit difficult. And what I propose, or what we propose, is that can we actually do this in a very open manner, so you're not restricted to only using proprietary software, or you're not restricted to use only a limited set of things. And there are companies who have actually been very successful in standardizing something. But what we wanted to do was we wanted to create an open source platform, so we can actually do that in an open manner, so other tools can be used, other libraries can be used, and we can actually deploy things in a different environment. And the result was having two very distinct and separate components called MLflow tracking, MLflow projects, MLflow models. And the last one, which was recently released, was MLflow registry. And we talked about tracking last time, and today we're going to talk about projects and model. And just to recap, the whole idea behind tracking was the ability for us to provide you very simple Pythonic fluent APIs that you just infuse your machine learning code with this very simple way to track parameters. You can track parameters in the machine learning parlance. You can track metrics that you actually create, depending on what machine language framework that you actually use. And then you can actually save a particular model, which we actually call a log model. And as a result of that, when you actually do all these, what you get later on is that you can actually use the MLflow UI to be able to peruse and investigate and compare all the different metrics that you actually have that you have created, that you have logged, all the models that you actually created, and you can look at the artifacts such as plots that you have saved. And it's very easy for you to not only track those, but it's very easy and a methodical way to compare and contrast how the needle actually moved from one parameter to the other one, or how different models actually compare to each other. And that was the whole idea behind tracking. And the tracking think of it, the tracking is a central server where things on the left-hand side are the producers of all the data, or the metadata, or the runs, or the experiments, which use the several APIs that we actually provide as part of the tracking to log everything on the tracking server. And things on the right-hand side, think of them as consumers that actually use the same API to consume the metadata, the experiment, the parameters, the metrics that you actually used, and present them in a digestible way, in an exploratory way that you can actually consume and make sense out of it. And you can relate that or convey that as a story of how the model evolved and what happened to it. And you can actually save your oldest metrics not only as a data source, but you can actually show them in the API on the console. So that's sort of the essence of the tracking. And one thing good about tracking is that you can actually use that locally, or you can actually use it programmatically by setting the environment variable. So that, in a very nutshell, in a quick 5-minute, was what we actually talked about in part one. And then we did loads of tutorials and on Databricks communication to show how you can actually use those. And so today what I want to talk about is MLflow projects and MLflow models, how they relate to tracking as well. And then by the end of the 3 series, you'll actually have an idea of how each of these work together. And you don't have to use, everything. You can use just tracking for everything. And then you don't have to worry about using models and projects. But these are added benefits that allow you to have distinctive and a selective way you can actually use these components. So MLflow project, what are MLflow projects, right? These are a conventional way that we have introduced, and hopefully by that becomes a standard, to package your machine learning code in a format that enables you to produce this particular runs anywhere. Now, one of the things that I stated earlier, and I did that in part 1, that I proposed, and I say that MLflow was built with the proposition and the principle of an openness. In other words, we actually wanted to support all the common libraries. You're not stuck only with 1 or 2, but a set of common libraries that most of the data scientists and machine learning developers actually use. And we also wanted them to be able to actually use different environments in which they can actually use this and deploy this particular project. And that requirement, that need in itself poses 3 problems, right? The first is that each of this particular tool will have its very generic way to encapsulate data and a very generic way to deploy those things. And secondly, people sort of run these experiments in different environments. Some run it locally, some run it on the local machine, some run it in the cloud, and some run it in notebooks that we will actually see. And the third is that even if you capture the exact data, and the parameters that you actually need, you might not be able to actually create the same experiment that you actually did when you were developing on your machine. In other words, the target environment might have a different set of libraries. The target environment might have different versions of the Python that you actually used or the language you use. And as a result, this poses an interesting challenge. How do you actually use machine learning difficult to produce? How do you reproduce a particular a set of experiments that you actually did it on your local machine, or you did it on your dev environment, and then you want to make sure that the same environment exists in your production environment, or the same environment exists when you want to share your particular project with someone. So if I create a particular project and I say, hey, Chris and Mary, here are the 2 projects that I've created. Can you guys actually run it and see what you think about it? And so one way to do that would be able to use this particular project as a way to share with my colleagues so they can actually run the experiments in the same environment. In other words, recreate the same environment, reincarnate the same project in the same environment so that they actually get the results. Well, so how do we do that? Well, the solution was that if you think of MLflow project as a self-contained unit of execution that bundles all the machine code that you actually need in order for you to train that, all the dependencies that you actually need to run the particular model, the libraries, the languages, the different configurations, all the data that you actually need, and the config specification, that way you can now run it locally, or you can actually run it remotely. And as a result, because MLflow can actually install and execute all this particular dependency in the target environment, you essentially are recreating that particular project in the target environment. So if I hand my project off to Mary and she went and executed this particular project, she would actually get the same results as I did on my local machine. So what's the secret behind that, right? How does it manifest itself? How does MLflow project specify so that we can do this recreation reproducibility? Well, there are 2 sets of things, right? As you can see, if you come from the Unix environment, which most of you probably do, this is just a simple directory structure that we actually provide on the GitHub, where under my directory called MLflow project, you'll have 2 files. One is called MLflow project, and the other one is called conda. And MLflow project is nothing but a specification and configuration instructing MLflow to say, okay, here is how you actually recreate my particular project in my target environment or in my local environment. I have a conda file that actually tells me what my dependencies are. And these are my entry points that I actually will use in order for me to actually recreate and run this experiment. And the entry point will have a command, will have some variables called training data that gives you the path of where the data is located. The lambda is all my arguments that I actually provide. I could have several arguments, but these are my default and the kind of type of argument it is. And then the command that is going to actually use to particularly train this particular model. So when I hand this over to Chris or Mary, that can actually just run this particular thing and it will recreate that. And the way they actually run is very simple. We provide the MLflow UI or the MLflow CLI to say you can run this particular Git repository that I've given you with this particular project, run it as MLflow git run, and then provide the arguments that I need. Now, if I don't provide the arguments, then it's going to use the default. But suppose Mary wanted to use her own set of lambda arguments, her own set of learning curves to actually recreate this particular model to see how it actually does, because I'm going to experiment that. So she could provide these particular arguments as well. Or you can actually use that programmatically. There's an API that says MLflow run GitHub repository, and the parameter is nothing but a dictionary with set of default arguments or the ones that you actually want. Or alternatively, you can, when you do a git clone of that particular project, you can cd to that particular directory and then just run in place, whereby you say MLflow run E, which is the current directory, and my entry point is main, and here are my arguments. So that's one. MLflow project is a way to express my project configuration and instructing MLflow to recreate this or reincarnate this particular project in my target environment. But more importantly, it is a second file, which is the conda.yaml. And the conda file, or this could be also a Docker file, by the way. So conda file tells MLflow to go ahead and create a conda environment. And then within the conda environment, here are my channels to use. The default is a way for conda to say, use my default way to get all the libraries and packages that I need. And here are my dependencies. My dependencies are, I depend on Python 3.7.3. So even though my local machine might have 2.3, but I don't want to run in 2.3 because I created this project using 3.7.3. So when Mary runs it, it's going to run with the Python install 3.3. I'll have scikit-learn, that's how I built the model. And I'm going to use pip to install MLflow. And then I need pickle because I use the scikit-learn pickle way to serialize the code. And I'm going to call my environment MLflow n. So that in essence is how MLflow encapsulate or formats a particular project. So in summary, what is a project? As I said, the project is nothing but a conventional way format to reproduce ML runs. And the way we do that is that we can actually provide a GitHub repository where you can plop in an MLflow project file that you express your project configuration. And it also defines a set of dependencies that allows people to reproduce the environment in which they initially trained. And then finally, we provide a set of execution in API arguments to run the particular project. And these could be a CLI, and they're available both in Python, R, and Java. And then you can support them by running locally, or you can actually do that by executing remotely on the Databricks server by specifying the backend, or you can actually run it on Kubernetes, which is experimental right now. So that, in an essence, is what the project is. It's nothing but a conventional way to express and convey to MLflow. Say, here's my project, go ahead and execute and recreate this environment by installing all the dependencies that I actually need. So what is an anatomy of MLflow project? What happens when I do an MLflow run with this particular URL as my GitHub? Well, number of things happen. The first thing it actually does, it does a GitHub of that checkout of that particular project into a temporary location on your machine or on the target machine. It creates a conda environment, it activates that. And the name of the conda environment is normally the MLflow run ID. It does that. And once it is actually activated environment, it will start installing all the packages that you actually need for it to create the environment in which it was initially run and experimented and sealed. And then finally, it's going to execute your particular program with that entry point that you actually provided, which is in this case was Python train.py arguments, and it's going to train the model right there. So essentially recreating the model with the same configuration that you actually had when, say, Chris created and shared that model with me. So you're probably asking, well, this is all good and fun. How do you actually build a particular project? Well, it's quite simple, really. If you think about it, there are a few steps, just like how it executes it. The first thing you do is you create an MLflow project file, right? and you populate that with your entry points. And by now, you probably know what those entry points are, and you provide the default parameters and so on and so forth. The second thing you do is you create a conda file. Well, how do you actually create a conda YAML? Well, you populate that with dependencies, but how do you know what your dependencies are? Now, if you have already created this particular model using the MLflow tracking API, then when you log the particular model, one of the things that we covered in part 1 was that if you look at the artifacts in the UI, there'll be an artifact called model directory. And under the model directory, you will have a file called conda, and conda.yml is the one that is what you actually want, unless you remember all of them. But this is the one that they actually captured, and that's the one you actually want to do. And you just take that, copy and paste, and put it in your GitHub as a second sort of file. The third thing you want to do, obviously, is you create a GitHub repository and upload those particular files in any other code and data and sources that you actually want that captivates and that captures what the project is. And then finally, test it by running the MLflow Git locally, and you can use it programmatically, or you can use a command line, and then share it on GitHub with anybody who actually wants. So this is sort of a good way to publicly share your projects that you actually have created over a period of time. So other people can just do a GitHub. It's a good way to show the resources. And one of the good things about the project is because of this way you can specify how the project should be executed, you can create what we call a pretty complicated multi-step workflow in your project specification to say, these are the way I actually want to create a multi-workflow. I can actually do, say, I want to do 3 sets of things before I train my Keras model. So I can load a particular file, let's say a CSV file from some location. I can use Spark to do the ETL. Once I'm done with the ETL and once I'm done the feature engineering, I'm going to save all my clean data as a Parquet file. And then I'm going to use Spark MLlib to load that file and then create a particular model to do that. Once I've done that, the output of my MLlib could be an input to my model training parameter. So then the next step would be go ahead and start training the Keras model. And then this sort of gives you an elaborate way to string together several workflow steps that you actually want. And then the driver can just look at each and every step and say, is it actually finished? If it's finished, then go to the next one, and so on and so forth. So you can create those in a fairly easy multi-step workflow. And what would a MLflow project file look like? Actually quite simple. Well, it's a bit involved, but you got all these different entry points you can actually see. And the entry points are, this is my conda environment. These are my different entry points. I'm going to go ahead and do the ETL. After I'm done with ETL, I'll create my ALS model. Then I'll do the train Keras. And then my final thing that I'm going to run is called actually main. And the main is the one that actually sort of invokes all these different arguments, all these different entry points, and you can take the results of those and feed them to the next. So you can actually create a fairly good workflow. So that, in essence, what MLflow projects are. Are there any questions on the QA that you want me to answer, or you guys are taken care of?
I think we're in pretty good shape so far. Thank you.
Thanks a lot, Chris. I appreciate that. Okay, so let's move on. So the next thing I want to talk about is models, right? And models, just like projects, are very similar. The motivation came actually from the same thing, is that we won't be able to deploy these machine learning models in a diverse environment. Remember, I talked about the ability for a model to be executed in different environments. And so this is one of the reasons why we actually wanted to have that. So the motivations behind models is no different from what it was for projects as well. You know, we wanted to have all these MLflow frameworks that we actually want to support, because our whole proposition was that we want to be able to have people use and combine the best of the tools available for them to do that. And we want to be able to, you know, serve them in different environments. And these in itself poses a number of problems. First is that models can be written with a wide variety of tools. And as a result, what happens is that you have to worry about how they're going to be used and how they're going to be executed in different environments. The second problem is that these models may be written, say, for example, by different frameworks. So I might I might write a TensorFlow model that I want to only run on Kubernetes, or I might run a scikit-learn model that I want to do both batch scoring on Spark, or I might write a Spark model that I want to create and have the ability to not only run on a Spark infrastructure or Spark cluster, but also run it on, say, SageMaker as an MLlib. And how do I do that? Well, if I wanted to support all that, what happens is that I end up having all these different end-by-end combinations to support my model on different servings. And it becomes the same problem that you actually had in projects. So the motivation is very similar. I don't want to have to support end-by-end different ways to say, for TensorFlow, use this kind of model to deploy it on Kubernetes, or for Spark, use 3 different ways to do it on SageMaker, to do it on Spark, and to do it on a Docker environment. So what was the solution? The solution, I think, was a way to say, can we actually have a convention unified modal abstraction, right? Think of it as an intermediate format that captures the flavor of the model that you want to deploy in a variety of environments, right? Think of a model as a conventional format for packaging so that machine learning model can be used in a variety of different environments. Think of models, more importantly, as Docker files for model, because if you have a Docker file, you can actually execute any application on one. But more importantly, the abstraction was that think of a model as a Lambda function. If you come from a Python environment, if you come from a functional programming environment, think of it as a Lambda function for a particular flavor of the particular model that we can actually deploy it in a desirable Python environment and just invoke its scoring function called predict. So this way I can actually take my Spark Py function and I can deploy it anywhere where it's actually supported in Python. So these intermediate level allows us to actually have a one layer, one format that all these other different formats can actually be used. And then we can actually have a target environment where we can actually store. And I think a good analogy that I would actually use for this is that those of you who are familiar with, say, an Apache Arrow, which is the way to internally capture how data is actually formatted or arranged in memory by all these different tools. Before Apache Arrow, all we had was this different way of formatting tools so they can actually share the data. But Apache Arrow gave a standard way to say, okay, here's how you're actually going to represent your data internally. So any of these tools can actually share. They know that this is an Apache Arrow format that I'm going to serialize and deserialize in one particular way. So their knowledge is very similar in that you actually have an intermediate layer that actually have all these multiple tools that can actually write to the particular format. So then I can, the consumer or the producer, or the consumers can actually know what flavor it is, and I can use that particular flavor. So their knowledge is very similar. Well, how does it do that? So what happens is that when you use the MLflow tracking API and when you use, say, MLflow TensorFlow log particular model, what happens at this point is that we create this directory for you, just like we create a directory, just like you need to create a project, we create this directory called ML model, this name of the model. Underneath, you will have everything you actually need to capture that. So you'll have the model file, and the model file will have 2 flavors in it. The flavors are normally the flavor that you actually use to log the model. In this case, it's going to be TensorFlow model. And underneath, you will have the directory that has the estimator, that has all the TFF graphs, all the variables, all the weights that you actually use to create this particular model. And you have a significant function that it's going to use to load the TensorFlow model. So this is usable by tools that understand TensorFlow model format. So if you deploy this somewhere on SageMaker or Kubernetes, it understands how to actually load the TensorFlow model and then use the predict function on it. The other one, which is actually quite powerful, which I thought about, which I said earlier, is to think of it as a Lambda function, is the ability to actually use the what we call the Python function or Py function model that can actually load the model anywhere in a Python environment. And by providing a pandas frame, you can actually do the predict function in this. So what's the result of this? Think of it this way. If I was actually using a Keras model and I logged the particular model using the tracking API, go ahead and MLflow log this particular model, what happens is that I actually create this particular model format and has 2 flavors in it. One is the Python func flavor and the other one is the Keras flavor. And when I have these two particular flavor, I can deploy them in multiple environments. So in an environment where Python is understood, I can just load that particular Keras model as a Python function and then just use the pandas input in frame to score the particular model. Or alternatively, if I just wanted to natively deploy it in the Keras environment, then I just use the Keras load model API, which will load the MH5 model as it's actually stored, and then supply the Keras input frame or whatever the vector it is or whatever the tensor it actually requires as part of the predict function, and it does the scoring. And this important way to represent these different flavors gives you the ability for all these different models that you actually create, a PyTorch, a scikit-learn, a Spark, a TensorFlow, Keras, with its Python function to be able to deploy them in a diverse environment where Python is understood. This is actually quite powerful, and we'll look at some of that in the lab. Hopefully we'll get time through that because we got about another 20 minutes or so. So to summarize, what are MLflow models? Well, they're nothing but packaging format for MLflow models, just like projects. They're nothing but any directory in which you actually have an ML model file. And they allow you to define dependency for reproducibility. So if I'm running this in a Docker environment, then I have a Docker environment that will capture the dependencies. Over here, the dependencies are, what do I actually need to run this particular model? We provide model creation utilities, so I can actually use MLflow model flavor to save the particular model, and I can use MLflow load model, or I can use MLflow load PyFunc model to load those utilities in a target environment. And we provide all these different deployment APIs for us to actually do that. So that, in an essence, really is, in a nutshell, MLflow projects and MLflow models. And MLflow models and tracking are very, very related, because the tracking API allows you to give you the utilities to actually create and save this particular models. So I think this is pretty much ends of a discussion. And what we're going to do now is go straight to the tutorials. So these are the projects we're going to work on, the tutorial we're going to work on, hopefully. By now, you've git cloned that particular URL that you actually have, and we'll go and you have installed or at least signed up for Community Edition, and we'll go straight into it and see how we actually fare. Okay. Can you guys see my screen?
Yes,
Yep.
sir.
All right. Is the font good enough? Can you actually see it?
Well, actually, I think we just see your desktop right now, Jules.
Okay. Let me just reshare it again. I think I'm running into. Let me see if I can do a new share. Let me try this. How about now?
I think so, yeah. So we can see a few windows, the one run project example.
Okay, so you can see the notebook now, can you?
Yes. Yep.
Okay, let me just do this here. Is the font good enough?
Maybe one.
Okay, let me go. How about now?
Yeah, I think that looks great.
Okay, brilliant. So I just want to, how many of you actually have already signed up for Community Edition? You had a chance to log in and go into the Community Edition. Any quick count? If not, I'll go straight into it. I'm assuming that people have created a Community Edition. They've logged in, and I'm going to just very briefly, very quickly give you a summary of what Community Edition is and how you can actually use it.
Yeah, I think a few people responded yes.
Okay, all right. So I'll just go ahead. I'll just go ahead and go straight into it, right? Assuming that you actually have loaded the DBC files. If you don't know how to load this file, you can actually go to your workspace, And what you do is do an import. And in this particular URL, you can either type in the entire DBC URL that you have in the GitHub, or you can actually just go and do a browse and then go to your GitHub directory. And click on this, done. And then an import. If you do an import, it's going to go ahead and import those particular files. There are a couple of ways to do that. So I'm assuming you actually have done that and you have a quick way to navigate that. The next thing we actually want to do is we're going to go ahead and create a particular cluster. I already create this particular cluster, but the way to create the cluster is you go to these tabs on the left-hand side or icons on the left-hand side. Click on this to create a cluster, type in your cluster name, and then choose the choose the 6.5 machine learning runtime so that it installs the MLflow and TensorFlow and Keras and all the libraries that you actually need. So you don't have to worry about creating those. Now, the reason my button is grayed out is because I already created a cluster. So when you create the cluster, it will start spinning stuff. And then when it's ready, what you'll have is a solid yellow, a solid green dot that you can actually attach to it. So my cluster has got this particular configuration, and so now let's do it. Right, the way you navigate around the cell is that you click on this particular cell. You can either hit Control Return, which will execute this particular shell and remain on the same shell, or you can hit Shift Return, which will execute this particular cell and then go to the next one. The other way to do that would be to actually use this particular drop-down ILO to actually run the cell or run everything above it, right? So we're going to run this. And the first thing we're going to do is just show you what this particular MLflow example looks like that I want to execute in this particular notebook. So I can click on this and let me open a new tab. And if I look at this particular example, this is an example that was created a long time ago with Mate, and this was a way to illustrate that. If you look at my MLflow project I talked about, again, it's a project specification that tells me this is what my entry points are. Here's my Conda environment, execute this particular command. I can look at now at the Conda file, and these are the dependencies that I actually need to create this. I can look at the train.py, and that's my Python program that actually trains a linear model that actually trains to predict the acidity of a particular wine. So it's a very simple thing, but the idea is I wanted to illustrate how you can actually do that. So let's go back over here and execute this. Right, so I'm using 1.7, and I'm going to have to run this because in Databricks I have to create this particular profile that allows me to create a token on my remote machine so that I can actually execute that. It's something you actually need on a Databricks community edition. You really don't need it on the local machine. And here are the parameters I actually specify. So for this particular thing, what I actually want is my alpha, which is part of the learning curve. These are the four arguments that I actually want to use. Here's my Git URL that I want to use. And then I'm going to use MLflow run to submit my run, right? This is the way I'm going to actually go ahead and execute this particular run. How are we doing with time? I've got 15 minutes. All right. So here, this is just a very simple loop. I'm going to go ahead and run it. And at this point, what this is going to do is, as I said earlier, it's going to go to the GitHub. It's going to download this particular directory. It will start executing and installing packages that I actually need on a particular temporary location. It will activate a Conda environment. It will go ahead and execute this particular run and then give me the results, right? Now this might take a few minutes for some of you guys. And the good thing about it is that if I don't specify any of these, then it's just going to use the default parameters. And so if you wanted to experiment a little more with this particular project that somebody shared with you on GitHub and you downloaded it, you can specify the arguments you actually need, and it's going to go start running this thing, right? And the reason it's taking a bit while because, you know, it for the first time, it's going to download everything, install all the packages, all the dependencies that they actually need in order for it to do that. On the local host, it's a lot faster, but that's what it is. Are there any questions on the chat?
Nope, I think we're looking pretty good. So let's keep chugging.
Lovely. And once this is actually run, what you will get is that it will actually create all these different runs and experiments, and then we can actually look at the UI to see what the metrics were, what is it you actually do to change the parameter, and look at what are the artifacts actually created. It's a simple example, but it illustrates the point that when you actually create this particular model, so when you create this particular project, you can share with other people. You can share it publicly with other people. The interesting question to pose is do you actually need this GitHub projects when you have model registry? And the answer is, I mean, yes and no. I think model registries are somewhere where you actually create different stages of particular model to keep track of central place where you actually have these particular models. The idea is the same as you can actually share the models and discover the models, but model registry is really more advanced feature. Projects is a good way for reproduce that. The whole idea behind project is that you can actually reproduce and recreate those environments. And that way you can actually share it using the best public source available, the GitHub. So here are my running parameters. I got my run ID, and now I'm going to go ahead and click on this UI that actually gives me at a high level what my runs are. So when I click on this, this is actually the result of all the experiments that actually ran with this particular parameter. And I can see that at high level, these are my L1 ratio. I use the alpha one. Since I use Lasso, these are my matrix that I actually created for all the 3 runs. I can go ahead and look at each and every run over here by clicking on that little up arrow. And now I'm in the MLflow UI. Excuse me. And as you can see, I actually have 3 runs that have all the parameters that I actually logged in. My metrics are, actually gives you a nice tabular way to do this. So my, very common regression metrics that I use, and then I can compare and contrast these things, right? I can actually do a compare to see what my model looks like. And this gives you a very nice tabular way. These are all my run IDs that ran. These are all my metrics that I got. This gives you a nice little scatter plot. I can actually use RSMME to see is there a correlation between the two. I can actually change this parameter to see what my scatter plot look like for L1 ratio. Should be pretty much the same because I've used the same ratio everywhere. But you can actually see that I can use all this different way to visualize this. I can look at my contour map. I can look at my parallel coordinates to see how each of these actually fared. So it's a good visual representation for UI to actually give that. So that sort of gives you the ability to actually do that. So let's go back to my run experiment. We actually run that. Another way to run that would be very similar to run this using projects.run. And projects.run is just another way to actually execute the same thing. They actually execute the same thing, so I'm not going to do that. But here we actually looked at some of the matrix. And as a result, you can actually create a fairly complex multi-step flow we actually looked at. Now let's look at the second one. The second one I'm going to do is a Keras example. And over here, I'm going to demonstrate how you can actually use this particular payload function. So here, I'm just going to import all the stuff that I need. Now I'm on the second notebook. I'll just go ahead and create this little thing called intro the warning. And I'm running TensorFlow 1.1. And you will see in my third example, how I ignored TensorFlow 1.1, but I use the TensorFlow 2.0 because that's the model I created. And that's the whole ability, that's the whole way to prove that you can actually reproduce and recreate environments using MLflow projects, right? So this is my TensorFlow running because this is what natively running. So I'm just going to create a very simple model over here. All it does is takes a Fahrenheit as a temperature and then predicts its Celsius. And it creates I'm going to create a very dense 2-layer model. Is it a linear regression? And one of the great things about MLflow tracking is if you have, hundreds of parameters, and if you have, half a dozen metrics, it becomes a bit cumbersome when you actually use the MLflow API to go ahead and log something, log parameter A, log parameter B, log parameter C, or log metric A, B, and C. What we have done is to make things easier for developers is that with each and every framework that we actually support, we have this notion of called autologging. And you just create one MLflow UI, MLflow log autolog or Spark autolog or Keras autolog, and it takes care of all the logging for you. So your code becomes very simple. Your code becomes very succinct. You probably use the same machine learning code that you use everywhere. And the only thing you actually need is to start to run with MLflow to instantiate a session with the tracking server, and then just use MLflow autolog. And these are some of the PI requests that are actually going on. So we should have that in the next couple of releases. And this is all my code. I'm doing this MLflow start run, creating a session with the tracking server. I get my experiment ID. I create my baseline model. I'm going to use this MLflow Keras.autolog. Remember, I'm not logging any of the parameters. Everything will log for me. I'll do the fit of the model, and then I'll do the prediction after I get the model. So let's run this. So this is going to train. And this is my driver. I'm going to create a batch of 10 epochs, 1,000, and then run the MLflow. So let's look at what this looks like. So what I'll do in the interest of time, I'm going to go ahead and go to my pre-run because it's going to take a little while to run it, to demonstrate to you that when I run that, this is going to train, and then I can actually run this to particularly train this particular model, and this go through all these epochs, and then finally it will give it the matrix, and then I should go to my runs, and I should see everything, right? All these things I didn't have to log individually. Keras autolog took care of all that. If I had to do all that, I would actually have to log I would have to have like several codes doing log this, log that, and so on and so forth. So it becomes a bit cumbersome. This allows you to say, just go ahead and do an autolog, and then I don't have to worry about it. It'll keep track of everything. The good thing it actually does, it also prints out the summaries and gives you a particular tag. And if you go to this particular model summary, it gives you the entire summary of what your layer looks like, how many of them had trainable parameters, and so on and so forth. You can actually look at the particular model. And this is actually a conda file that actually has 1.1.5 ran, right? And then I can look at my mean square error to see what it looks like. I can actually step through that, get a nice little smooth curve. I can compare and add another one here, let's say loss. And it gives me the ability to see how my mean square actually progress with each and every epoch is actually approaching 0. So that essentially sort of gives you the ability to run this Keras model running in natively. Now I'm going to do something else over here just to show you that here's my prediction for the temperatures. And you can see the model is not very good. Right, it just should be close to 0, and this should be close to 100. So what is the thing we actually do? Is it because of 1.5? Is it because I don't have enough data? So let's go and look at the third example where I run this particular project that I created, that I shared with someone, and I'm going to download that. The changes I've made over here is just one thing. I'm running TensorFlow 2.0 rather than TensorFlow 1.1. So when I ran this particular model, what does the project look like? Let's open a new tab. Very simple file. I have my conda environment. These are my parameters that actually train. By default, I'm using 10 and the epochs of 100. I can look at my conda file. And if you look at the conda file, I have all this dependency. Now I'm using TensorFlow 2.0, right? So what will happen over here is that when I actually run this particular project, it's not going to use the TensorFlow 1.1, which is running natively, but it will recreate my environments with TensorFlow 2.0 and all these new dependencies, and it will actually run this, train this particular model into the prediction in this particular project environment. So let's go back over here and then run this, right? MLflow 1. I'm running this particular GitHub, the same thing I did that before, and I'm going to run this particular parameters. And then when I run this, I get this particular UI. I get this, my run ID and my metrics. And the next thing I'm going to do is to prove you that it actually ran 1.7. Here's my 2.x flavor. I'm going to load this particular model. Remember we talked about I load this Keras as a log model, and I'm going to load this back as a Python function model. And this is how you actually load the model. You actually provide the URI, you load the particular function, and so you loaded this particular backend function. And then I did the prediction. And when I did the prediction with this new particular model that ran in 2.0, I got a fairly good prediction, right? It was much better. And the only thing I changed was the most recent one. And I can make this particular model, far more accurate by either having more layers, increasing the data, doing other parameters, and start running this experiment over and over again to get a better metric. And then this sort of proved that the reproducibility of the ML project is that even though I'm running TensorFlow Keras in my second example, the third example actually did TensorFlow 2.0, and it downloaded the TensorFlow 2.0. It recreated this particular environment to do that. And if I went back to the runs and I went to this particular directory for my run, and I looked at the particular run, and I looked at my model, conda.yml, it's TensorFlow 2.0. So it essentially downloaded the TensorFlow to recreate this particular model. So I think we are actually coming close to the hour, and I have taken up almost everything. Like I said, it's always difficult to go through all these particular examples, but the examples are there for you. The examples are there for you to run tonight or tomorrow. And if you have any questions, you can always send me email or DM me or connect me on LinkedIn.